thank you very much. It's a great honor to be here today. A little bit frightening, but I will try to explain you this very complex element, which is the carbon neutrality of aviation. So first of all, I will begin by showing you this chart. I'm sure you've already seen that. Aviation is committed to carbon neutrality in 2050. Okay, that's good. Everything is set. Now, let's shift to another thing. We show this example showing that we have a roadmap in order to meet this neutrality in 2050. This roadmap is based on three main pillars. Three pillars that are fully complementary. It's not one or two. It's always the three that will have to be activated in order to meet this neutrality. First of all, it's the technology. Of course, the best fuel is the fuel that you don't burn. So the first item is to drastically reduce the fuel consumption of all the aircraft, all the future aircraft, which is already a great challenge, and I will show you some examples just after. The second one is to make all the operations of the aircraft more efficient, especially in the air. It's quite funny to know that, but the aircraft, they don't fly in straight line. They make a lot of a lot of variation in a flight mode, so that having this optimized flight route can allow a gain of some percent, higher than 10% of CO2 emission in the future. And then the last part will be the low carbon energy. And behind this word of low carbon energy, you find a lot of things that can be done. Sustainable aviation fuel by biofuel, e-fuels, hydrogen, electricity, and all that. And I will show you that, unfortunately, there is not one single bullet, and we will have to develop all these pathways in order to meet the neutrality. I could have stopped here because everything is said, but I will show you some examples, and I will show you how difficult it is. I will show you that it's quite impossible to reach this neutrality, but I will show you that we will succeed. That's important. It's very difficult. There is no silver bullet. There is not one technology that will solve everything and allow us to have this carbon neutral aviation. But by adding all these small steps, all these technologies, there is a way in order to reach carbon neutrality. Safran is a major technology provider for aviation, and clearly you've seen the three pillars for decarbonation, and we have the development on these three pillars. The first one is a disruptive technology, and you see here an example of what we call the RISE project. The RISE project is a disruptive engine, and the goal with this engine that is developed with our partner GE in the frame of the CFM cooperation, this engine, the target is to reduce by 20% the fuel consumption at the engine level, which means with all the optimization around the aircraft, around 30% of fuel consumption reduction of the aviation. And I will show you that it's quite a challenge. The second one is to enable the transition to low carbon energy, biofuel and things like that. And I will show you some examples. And we've made a lot of demonstration in the past 5 years, I would say, in order to show that it's possible, and in order to show all the potential of this. And the third one is to build the blocks, to develop the blocks for more electrical aircraft and up to full electrical aircraft. And I will also show you some examples of that. But before that, I have to say a few words about aviation. I will show you all the specificities of aviation, which leads to this complexity in terms of decarbonation. First of all, aviation is already an industry with tangible decarbonation results. We are not beginning our journey in terms of decarbonization. We've made a long road in order to go to the level at which we are today. Just an example, today the CO2 emission of aviation has been reduced by more than 80% in comparison with the first aircraft in the 50s. The mean CO2 emission per passenger kilometer of the aircraft in operation today is less than 50 grams per passenger kilometer, which is already a very low. If you translate it in terms of fuel consumption, is less than 2 liters per kilometers and per passenger, which is quite efficient. But as we go to long distance, at the end, the volume of CO2 is high. It's not because of the inefficiency of the aircraft, it's because of the long travel. And clearly, when you have already made a reduction of 80% of the CO2 emission, going down by 40 by 30 by 20% is far more difficult. It's always easy to have the first percent. It's always difficult to have to reduce the last one. So that we are in a position where it will be very, very difficult to have the remaining percent, and that's why we have to go to disruptive technologies. The second element, which is very important, is that aviation is characterized by long-range journey. Typically, 70%, the flight of more than 1,500 kilometers represent 25% of the flight, but more than 70% of the CO2 emission. Which means that if you develop a technology dedicated to small aircraft, dedicated to regional aircraft, it's very interesting in terms of air quality at the airport. It's very interesting in terms of decarbonization of short-range aircraft, but it will reduce CO2 emission of aviation at a maximum of 30%. And all the remaining 70% will have to be decarbonized by other way. The third element that we have, the third difficulty that we have, is the safety. Decarbonization is our key priority, but we will never make that by reducing the level of safety. Aviation is the safest way of transportation today. It will remain in the future. Clearly, there is no way we'll reduce this high level of safety of all the aircraft. Another element of our specificity is the weight. Our main enemy is weight. And you have just an example here. United Airlines estimated last year, I think, that they were spending more than $1.2 million in fuel only to carry your phone in the aircraft. The weight of your phone is a cost of $1.2 million for this big airline. Which means that if you want to develop a new technology that will increase the weight of the aircraft, clearly, you will have to take this into account in the final balance. And if you reverse the point, all the technologies that we will develop will have to be very, very efficient in terms of weight reduction. And that's a very important constraint. And last but not least, the impact of aviation on climate change, on global warming, is not linked only to CO2 emission. It's also linked to what we call the non-CO2 emission. Non-CO2 emission are all the emissions in high altitude, typically the contrails and things like that, that induce a global warming. And these effects are at least at the same level of magnitude than the CO2 effect. Once again, if we succeed in reducing by 100% the CO2 emission of aviation, we will have made half of the journey. The non-CO2 effect will remain. On the contrary, it means that all the technologies that we will develop will have to reduce CO2 emission, but also to reduce this non-CO2 effect, and typically particles emission, NOx emission, and things like that. And you have here in this room experts of that technology. You can go to see IPSL, CNRS, ONERA. They will explain you all this in detail. Having said that, it means the main conclusion is that the optimal energy in the future of aviation will have to be safe, will have to be low weight, will have to be compatible with all types of aircraft, because typically the life duration of an aircraft is around between 20 and 25 years, so that if you build a technology that is not compatible with current aircraft, you will have to wait 20 or 25 years before a generalization on the market. This energy will have to be compatible with existing fleets, and this technology will have to be low carbon, but also reduce the non-CO2 effect. OK, mission impossible. It's clear that we have a lot of constraints in aviation. We have a lot of constraints, which means that that's why aviation is always considered as a hard-to-abate sector in terms of transport. It's far more difficult to decarbonize aviation than to decarbonize other sectors. Or at least the technology will have to be far more complex than for other technologies. Now I have convinced you that it's impossible. I will show you why we will do that. First of all, when we speak about sustainable aviation fuel, it's really already a tangible situation. It's a tangible element. We already have technologies that are fully compatible with all the aircraft. You can today take an aircraft fueled with sustainable aviation fuel without any modification of the aircraft, without any modification of the operation, without any modification of the safety. It's fully safe, and it can be done in any aircraft, any airport, any type of flying objects in the world, which is already a very, very disruptive result. We always say that well, it's transparent so that we don't see all the effort behind that. But today, it's already a result. All these SAFs, the sustainable aviation fuel, they don't reduce CO2 at the exhaust of the engine. It's based on the life cycle, which means that the CO2 that you emit at the exhaust of the aircraft has not been taken in the ground and put in the atmosphere where it accumulates. It has been taken from the atmosphere by the plants, and then the transformation of these plants make the CO2, the carbon, goes back in the atmosphere. So the reduction of CO2 is based on the whole life cycle and not at the exhaust of the turbine, which is quite complex to explain and which leads to a lot of difficulties in terms of qualification of that. How to be sure that we have this full life cycle reduction. How to be sure that we don't have any side effect that will increase the CO2 emission on the global life cycle. It's very important, and we work a lot on that. So I will just show you two elements that we are sure. A lot of things remain uncertain in that field, but we are sure of two things. The first thing is that without the development, a massive development and immediate development of sustainable aviation fuel, we won't be able to meet our target. That's clear. That's clear. It's not with the technology, it's not only with the technology that we will meet that. Electrical aircraft will remain dedicated to small aircraft. Hydrogen aircraft, we are working a lot on that, but they will take time in order to come to the market and will be limited on the beginning to regional or small range aircraft. So typically, if we don't develop massively sustainable aviation fuel, and especially biofuel, we won't be able to meet our target. But the other statement, which is a side statement, that we also know that putting all our hopes only in biofuel will be very, very risky, I would mean. Because we all know that biofuel, biomass, is limited in terms of availability. We all know that biomass is needed for a lot of sectors, a lot of other modes of transport, but also for green chemistry, but also for heat, for energy, etc., etc. So that even if we have a lot of biomass which is available, everybody will want it. So that putting all our strategy only on that type of energy will be too risky for us. And that's why we have to find ways to enlarge the type of feedstock that we will use. And how can we enlarge it? First of all, by finding new type of biomass, and typically we have some work led on algae, led on new type of crops in order to be able to be transformed to biofuel, but also by shifting to another feedstock, which is low carbon electricity. And that's here that you will find hydrogen, and that you will find especially e-fuel that I will show you just after. And clearly, when I say that, you are now convinced that there is no opposition and no competition between hydrogen technology and sustainable aviation fuel. We have made some communication in the past where people thought that the future of aviation will be hydrogen. Yes, the future of aviation will be hydrogen, but also biofuel, but also e-fuel, but also electrical aircraft. There is not one single bullet. And you have to see hydrogen and electrical aircraft as a way to reduce the pressure on sustainable aviation fuel, not as a way to replace them. We will make all that we can with this low carbon energy, and then we will develop all the other technology in order to feed the specific needs in terms of low carbon electricity. And typically, that's here that's what I've just said. Clearly, when we say that hydrogen will be at the center of the decarbonization of aviation, that's clear, and that's a fact. But hydrogen can be used in order to produce biofuel, can be used directly as hydrogen in new aircraft, or can be used by transformation in what we call the e-fuel or power to liquid and things like that. So another statement that is very important, developing low carbon electricity production, developing hydrogen production, typically, it will be key for the future of aviation. And even if we don't succeed in building this new hydrogen aircraft in time, and we put all our forces in order to meet this target. But clearly, we are in a technology that is really new, that is disruptive, so that potentially we won't succeed. Even if we won't succeed in developing the hydrogen aircraft, hydrogen will be needed for the decarbonization of aviation. So it's typically a no-regret choice. What is what we call PTL or e-fuel or something like that? The goal of this type of product is to transform, to use low carbon electricity in order to produce hydrogen, to, I would say, use CO2 that have been captured either industrial fume or in the atmosphere, and then combine them in order to produce a fuel that can be used in all the aircraft. It seems to be quite science fiction, but it works. It works. We have to work still on the global efficiency of the process. We have to work in the reduction of the cost of this, and very important, we have to work on all the feedstock, which is clearly low carbon electricity, which is the key in the future for all these products. But we work on that, and you have here a snapshot of Ineratec, the product Ineratec, which is a German startup in which Safran has invested a few years ago. And clearly, we are working with other industries, and we are still trying to find new disruptive companies in order to support our journey in the decarbonization on specific bricks, such as direct air capture, such as transformation like this, in order to help them come to the market and support the decarbonization of aviation. So don't try to read what is written here. It's only just for the kids. You just watch the color. In this table, we try to put, with all the technologies, with all the type of energies, based on some criteria, such as the type of raw material, the availability today, availability in the future, cost, technical maturity, etc., etc. We try to put all the type of energy for aviation: biofuel, future biofuel, e-fuel, hydrogen, and things like that. And we put in green where there is no issue, yellow still to work, red very difficult to overcome. The only thing that you have to see in this chart is that there is not one column that is fully green. Not one. Which means that there is not one silver bullet for that. We will have to work on all the technologies, and we will have to develop all these technologies. And so, to conclude, clearly the future of aviation will be diversified. Will be diversified because we will have biofuel, we will have e-fuel, we will have hydrogen, and we will have electricity, which is very complex for us. It's a real traumatism for aviation, because for 50 years, we had the same fuel everywhere in the world for all the aircraft, and all we have said to the newcomers, to the new student and new person that come to our industry, we always say them, please don't touch anything. Don't change anything. It works. Sometimes we don't know why it works, but it works. So you don't touch anything. And here, I'm saying to you, we will change everything. So it's a real traumatism for aviation to have this shift, but it's necessary, and we will do that. And typically, we will have this diversification, but we will have also a specialization. Well, this phenomena is known in all the sectors. For road transport, for instance, you will have electric aircraft for small vehicle, biogas for road transport of big trucks. You will have hydrogen for some vehicle, typically a specialization of the energy according to the mission. It will be the same for aviation. Very small aircraft will shift to electricity. Bigger aircraft will shift to hydrogen, either in fuel cell or in turbine. And then bigger one will remain on liquid fuel, but this fuel will change to biofuel and e-fuel. This will need huge investment, because in the airport, for instance, you will have to fuel all the type of aircraft, so you will have to build infrastructure for electric aircraft, for hydrogen aircraft, and keep the fuel, the liquid fuel for this element. One important point here is that this chart is quite misunderstanding, because it seems that hydrogen will cover a huge range of aviation. So just keep in mind that the I would say, urban air mobility, sole propulsion, commercial, regional aircraft, and the beginning of short-range aircraft represent less than 30% of CO2 emission. So we'll have a diversification, but liquid fuel, based on biofuel and e-fuel, will remain the majority, even at long term. And so, as a conclusion, we will have, in the future, a diversified energy. We will have a specialized energy, but what will be common, clearly, the two elements that will be common in the future, and we have to really keep all this in mind, is that it will be safe. We won't reduce the level of safety even by changing that. And it's a real challenge. And when we discuss about hydrogen aircraft, you can imagine that keeping the high level of safety with this totally new type of energy will be a real challenge. And the second element is that it will be ultra efficient. And it's another thing that people tend to forget, is that even if we have an energy that is low carbon, even if we have an energy that is zero carbon, this energy will be rare and will be expensive. So that this shift to new low carbon energy will require, clearly, a massive reduction of the fuel consumption of this aircraft. So that all the work that has been done in the past in order to increase the efficiency of the aircraft, we have to go one step further, and we have to develop this ultra-efficient aircraft by disruptive technology in order to be able to develop this low-carbon energy. Once again, it's not technology versus low-carbon energy, it's technology supporting the low-carbon energy, and that's fundamental. We won't do that alone. Clearly, we won't do that alone. Even if we have a huge budget, and 75% of the budget of Safran is dedicated to the reduction of aviation environmental footprint, we will need, and we work with a lot of partners in order to do that. With collaboration in terms of R&D, and once again, you have here Onera, you have here some of our major partners. We work in the field of biofuel with Total Energy, that is also here, but also by working with newcomers. And clearly, having new companies with disruptive technology will be key for us. You just have here some example. We invested in Cranfield in the UK. We invested in Ineratech in Germany. We are discussing with a lot of companies in the field of direct air capture, in the field of new energy. My colleague, which is here, has recently built a very impressive initiative, which is Explore H2, in order to gather startups in the field of hydrogen in order to try to build these new bricks in order to develop the hydrogen aircraft. Clearly, it's by working together, by working with all the new technologies, that we will be able to meet this ambitious target of aviation decarbonization. And that's why we are here today. It's in order to show you that, yes, it's impossible, and that's why we will succeed, and we'll succeed together with all the persons that are just like us, convinced that in the future we will still need to fly, and that aviation will be needed in the future in a sustainable work. Thank you for your attention, and please, I will be here for any question if you want.